In this video, I'm going to lay out some ideas about the gravitational force holistically. And then what we're going to do is we're going to move over to the electric force to do some parallel work. So here we go. There's going to be a lot of comparisons. So the gravity force. We know that the gravity force has, let me actually go back to the color it's easier to see. Fg, the magnitude of Fg, let's just use magnitude here because that's what I care about. Big G, m1, m2 over r squared, okay? So let's say I have a mass here floating in space. Maybe it's the Earth. I don't know. Yeah, sure, it's the Earth. Cool. So right now, is anything experiencing a gravitational force? And the answer is no, because there's nothing there. Now you're going to say, oh, there's people there on the Earth. Sure, but I don't see them, right? For us to feel a gravitational force, I would have to put another mass in the space around it. But here's the thing. I'm not going to do that. What I'm going to do is think hypothetically, right? So we're not actually going to put mass there. We're going to imagine what would happen if I were to put a little bit of mass at that location. Now, I didn't put the mass there. I'm just hypothetically thinking what would happen if I were to put mass there. And then we would know that it would attract, right? And it would experience a force in this direction. Now, I'm not labeling that with a force because there's no force, because I didn't put mass there, right? In fact, you can kind of think if I were to put mass anywhere along this line, it would experience a force inwards towards the center of the Earth like that, right? If I were to put a mass there, this would be the path that it would follow, right? If I were to put, I'm not going to, hypothetically, if I were to put a bit of mass here at this location in space, what would it do, hypothetically? Well, once again, it would track inwards towards the Earth like this. Boom. I guess I could put a couple of other arrowheads there so we don't think of them like that. If I were to put a little bit of mass here, what direction would it experience a force? It would experience a force like this inwards. Same thing here, 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 and here, right? These all show the hypothetical path a bit of mass would take if it were placed at rest at some point near the Earth. Okay, cool. But there's no forces because I didn't actually place anything there. What am I talking about? Well, what I'm talking about is this set of vectors. This set of vectors describes hypothetically what would happen to a bit of mass in a region surrounding the Earth. What this is, well, and by the way, how many more lines could I draw? Right, I could have drawn an infinite number of these lines because this is just an imagining thing, an imagining tool so that we can hypothetically understand what's going on. So what is this? Well, we're going to give this thing a name. We're going to call this the gravitational field. We've discussed the gravitational field before, but we've never really defined it. So what is the gravitational field? Well, it's the set of vectors that show how a hypothetical mass would be affected by the gravitational force of a source mass in a region. Another way you can kind of think about the gravitational field, it's not a great description, but some people say this, it's like an aura around a mass that shows its area of effect and what happens due to that area of effect. This is a slightly more technical definition, but that's the concept. Now, I've drawn a flat picture here, but you have to understand there's also these vectors going three-dimensionally as well, but I'm stuck to 2 dimensions. So what are these things here? Well, we're going to call each of these lines here, when they're not lines really, they're rays, right? But we're going to call them gravitational field lines. And so what's a gravitational field line? This shows the path a hypothetical we'll give a name to this thing, test mass. So shows the path a hypothetical test mass would take due to the gravitational effect of a source mass. Or a source mass is plural, it doesn't have to just be one. Okay, but we'll get there, it's a little bit more complicated. So, shows the hypothetical path a test mass would take due to the gravitational effect, effect with an E of a source mass. And notice that if I had to describe what this set of vectors did for the gravitational field, that this set of vectors converges towards the source mass, right? That's because the gravity force always attracts. All right, cool. So we have a gravitational field. Wait a second, I've heard that phrase before. That's right, because we talked about something called the gravitational field strength. And what was the gravitational field strength? What symbol was that? Oh, that is our friend little g, right? Not big G, little g. So where did we see the gravitational field strength? We've been using that in our magnitude of the weight equation. That was m times g. But what m was that? That wasn't the source mass. That's like my mass. If I'm trying to feel, if I am in a gravitational field, I multiply my mass times what the strength of the gravitational field is at that location in order to figure out what my weight is. So if we want to define this a little bit differently, this little g is the ratio of the gravitational force per unit mass. Actually, let's say the ratio. It's just the gravitational force per unit mass at a location in space. Okay? And so that m is our test mass. I'm going to give that a little variable here, m naught, m sub 0. Okay? So I'm going to do that. Because I don't want to make you think that that is the mass of the source. So actually, if I look at this equation here, one of these is the source mass, and one of these is the test mass, the thing that you put in the field, right? And we saw this before, such that if I solve this for Fg over m naught, which I had here, notice what that would be is big G, mass of the source, over r squared. And that is the equation for the gravitational field strength at some place in the gravitational field, right? Notice there, the bigger the mass is, that's the source, the stronger the gravitational field is, and the further away you are, the weaker it is, which should make sense. If I'm on Earth, if I go off Earth, like to say this to I don't know, in a space shuttle, gravitational field strength gets weaker. If I'm on the moon, the gravitational field strength is weaker because the source mass is less. The mass of the moon is less than the mass of the Earth. And we talked about this before, this idea of gravitational field strength. Okay? Big G, mass of the source over r squared. Everyone hopefully comfortable with that idea. So, why do I go through all this? Well, I go through all this because we have very similar vocabulary when we're talking about electrical charge, right? So let's do this. Fe, K, Q1, Q2 over r squared. Let's say I had a charged object here. So that's my source charge. Q source, right? So, is anything feeling a force here? And the answer is no, because there's nothing else there. We need two things in order to feel a force. But if I were to, I'm not going to, but hypothetically, if I were to put a little bit of of charge here, it would feel a force, right? What would happen to the little bit of force there? Okay, hopefully now you've said to yourself, well, we need more information. All right, I'll give you more information. Let's say that our source charge is positive. There you go. That's the information you needed, right? Cool. So my source charge is positive. So if I were to put another little bit of charge there, what would happen to it? Uh-oh. Uh-oh. We have a bit of a problem here because I don't know if the little bit of hypothetical charge I place here is positive, it would be repelled away. But if the little bit of charge here is negative, it would be attracted. Now, let's go back to this picture of the gravitational field. The gravitational field picture is really nice because I can look at it and know what's going on, that those lines and those arrows represent the path a mass would take in that region. I'm going to have a problem here because positive particles in this region would do different things or opposite things than what negative charges would do in this region. So what's the person to do? Well, here it is. I know that a charged particle placed here would move somewhere along this line. And I know that if I placed it anywhere in this region of space, this is what would happen, right? But this is not really a great picture because I don't know the directions of what's going on. This is not a set of vectors, it's a set of lines. But what we are looking at, folks, is what we're going to call the electrical field, or the electric field. Actually, let's just go electric field, not electrical. The electric field, right? So the electric field. So what do you think is going to be the definition of it? Well, hopefully you're looking back at the definition of the gravitational field. It's going to be very similar. So it's going to be the set of vectors that show how a hypothetical. Now we need to stop because here's the thing. When the electric field was first defined, someone made a choice. Because what I wouldn't want to do is put arrows going in both directions on this line. That'd be silly. That's like the scarecrow in The Wizard of Oz, right? Which way to go? That-a-way. And he points in both directions at the crossroad on the yellow brick road. Not helpful, right? So when this was first defined, someone made an arbitrary decision. And we are going to make that same decision because we want to conform with the rest of what physicists believe, right? Because when we look at an electric field, it's supposed to convey very specific piece of information because we've decided that's what it's going to convey. So what decision was made? The electric field was defined as the set of vectors that show how a hypothetical, and I'm just going to write this in big block red letters, positive charge okay? So the set of vectors that show how a hypothetical positive charge would be affected by the electrostatic force of a source charge in a region. That is the definition of the electric field. Therefore, I can go back to my picture and I can put in the arrowheads. Okay? Because that's what a positive charge hypothetically would do if placed somewhere in this region. So, what are we going to talk about next? Well, if we're following along parallel in the notes, hopefully you guessed, what I'm going to do is define these things as something called electric field lines. So what's an electric field line? It shows the path a hypothetical. And now go back to my red because I want to make sure we know this. Positive test charge would take in this region. okay? Clearly then, a negative charge moves oppositely along the path, right? And so I don't need to show both what happens to the positive and negative, because when I'm reading an electric field line picture, I say, oh, that's what's going to happen to a positive, and negative, the opposite thing happens. So there we go. That's the electric field line. We're going to say a lot more about electric field lines a little bit later, but shows the path, a hypothetical positive test charge. By the way, let's give that, we'll call that Q naught, positive test charge, right? Would take, or just, that's what the test charge is, it's Q naught, right? Would take in that region of space. Well, what that means is this is the electric field surrounding a positive source charge, but if I had a negative source charge, the electric field would go in the opposite, or seem to suggest that things would move, or positive charges would move in the opposite direction. So there we go. That is what the electric field surrounding a negative source charge looks like. Okay, so they're a little bit more complicated than the gravitational field because there are two flavors of charge. All right, so what's going to be next? Well, if you guessed it, hopefully you guessed it correctly here, thinking parallel to the notes, what we're going to talk about is something that we're going to call the electric field strength, which is sometimes called the electric field intensity. Actually, I'm just going to stop for a second because I want you to know, just very specifically, electric field lines are not real. They are like an imagination tool that physicists use to kind of figure out and make predictions about what's going to happen in a space, right? So they're not actual things. All right, so I just felt I needed to say that. But electric field strength, well, in the same way that the gravitation field had a strength, so does the electric field. All right, well, what are we going to do? Well, we're not going to use little e because we've already used little e, but you know what we haven't used? Capital E, right? So capital E, the electric field strength, the electric field intensity. Now, I should note that the electric field strength is a vector itself. Now, I kind of skirted the truth on this. Technically, the gravitational field strength is a vector itself. We've been using it as a magnitude all this time. But since it always pulls inward, I wasn't too concerned about that. So let's just be very blunt there. It's the electric field strength. There you go. Now, if we're using parallelism, what is that going to be equal to? Well, the gravitational field strength was the gravitational force per unit mass at a location in space, right? So our example there, right, on Earth, on average, little g, magnitude, was about equal to 9.8 newtons per kilogram. So for every kilogram of mass I put at that location in space, it felt 9.8 newtons of force, right? And that's on Earth. On the surface of the moon, that's approximately 1.67 newtons per kilogram, right? Newtons per kilogram if we're doing units there. Well, what would the electric field strength be equal to? Well, hopefully what you figured out is that the electric field strength, and I'm just going to do magnitudes here because we're not going to get too bent out of shape. And notice here I'm doing magnitudes. Why didn't I really have to worry about magnitudes here? Well, mass is always positive, and so I didn't really have to screw around with that all that much. But here we're talking about charge experiencing a force. So the magnitude of the electric field is going to be defined as the electric force per unit charge at a location in space, right? So I'm going to write that in words. The electric force per unit charge at a location in space. So what are going to be the units then, the electric field? Well, the units of the electric field then are going to be newtons per coulomb, right? Newtons per coulomb. So as an example, if the electric field at a certain location in space has a magnitude of 1,000 newtons per coulomb, for every 1 coulomb of charge I put at that location in space, it experiences a force of 1,000 newtons. There you go. So we've got this new equation here. Sometimes you write this in another way, that the magnitude of the electric force is equal to the charge that's at that location in space times the electric field intensity or electric field strength. Okay. Notice here we don't have to deal with directions because this is just all magnitudes, but I'll just put the magnitude, the vector signs over that anyway, just for sake of completion here. We don't have to do that when doing problem solving. So how do I know what directions they go? Very simply, if the source charge is positive, Fe is parallel to E, meaning that the electric force is in the same direction as the electric field, right? Because that's how it was defined. And if Q naught is negative, the electric force is anti-parallel to E, right? Because negative things go in the opposite direction as what the electric field suggests. So we're going to try some problems with that, that notion. So I'm going to do one sample problem for you here using that. And then in the next video, we're going to talk about more complicated electric field pictures. So our example, let's say at a location in space, there exists an electric field of 4,000 newtons per coulomb to the right. Okay, part A plus 6 coulomb charge is placed there. Okay, and B, an electron is placed there. Right? And in each case, I want to know the force. So here, first thing we're going to do is write down our equation, Q naught times E, right? And first what we're going to do is we're going to calculate the magnitude of the force. So 6 coulombs, the electric field is 4,000 newtons per coulomb, and this is 24,000 newtons then, right? Nice, simple problem there. So what's that direction? Because that's just the magnitude. Oh, here, Q naught is positive. Therefore, since E is to the right, therefore, Fe is to the right. And if I had made a declaration, then I could use that declaration. Cool. B, here, Fe equals Q naught times E. What's the charge on an electron? Well, the charge on an electron is either negative 1e, or it is negative 1.6 times 10 to the negative 19th coulombs. Which of those am I going to use? Well, I'm not going to use the elementary charge because this is in coulombs, newtons per coulomb, so I want all my units to work. So I'm not plugging in the charge here. The magnitude, rather, is the sign of the charge or the flavor of the charge, times 4,000 newtons per coulomb. And what's that? 6.4 times 10 to the negative 16th newtons, right? That's the magnitude. But here, since Q naught is negative, since E is to the right, given in the problem, therefore Fe has to be opposite that. Therefore, Fe is left. And if there was a declaration, I could assign that, right? Actually, we probably should say that here, Fe has to be in the same direction, therefore Fe is to the right, okay? And that's the sort of analysis that we're gonna wanna see every time we're doing this electric force versus electric field idea, okay? Now, one last thing, in the same way that we had little g is equal, or its magnitude is equal to big G, the mass of the source over r squared, what would the electric field magnitude be if we have a source charge? Hopefully you can see very similar, K, Q of the source over r squared, where that would be like that as well. Very similar. We're not really going to use this equation except just as a conceptual idea. and it should make sense based on the parallelism and the argument that I've been making. So in the next video, we're going to talk about more complicated electric field pictures, as well as say some more things about electric field lines.